Welcome to module 9, lecture 5. We will continue with special concrete and we will first discuss the remaining part of the fiber concrete, followed by roller compacted concrete. So, what was left was short random fiber. We are looking at aligned fiber to understand the basic theories, flexure, workability and durability of fiber concrete, and then we will look at roller compacted concrete. Now, if you recall from the last discussion, we are talking about the crack width in case of aligned fiber. Now, the crack width would be actually crack width, if you remember, it was a continuous system and then the cracks came in between, and we talked about the strain as well. The strains, the matrix should have now shortened a little bit. Matrix was earlier at epsilon mu strain, matrix was at epsilon mu strain. Now, it is part of it is only at epsilon mu, that is this point, and rest of the place it is less than epsilon mu. So, actually the matrix would have shortened a little bit, and the stress from the matrix went into the fiber, and therefore, fiber strain actually is higher. That is what we have seen in the last. Fiber strain increased, and the stress in the fiber delta sigma fiber we said was actually epsilon sigma mu Bm divided by, this is the stress that has to be taken divided by, this is the stress that has to be taken divided by Bf. So, that is the stress divided by taken. So, this is the extra stress. If you divide this by Ef, you get the, if you divide this by Ef. So, epsilon extra, additional strain we get by dividing by Ef, and then we said that the additional strain will be actually alpha epsilon mu, additional strain will be alpha epsilon mu. At this point it will be alpha epsilon mu, and this was already there. So, total strain will be, this is the additional strain. So, at this point it is 1 plus alpha epsilon mu at this point. So, that the average is half alpha epsilon mu. So, that is the strain in the, there is the additional strain in the fiber, therefore, there is an elongation, but the matrix actually. So, the crack width will be equals to the strain in the fiber minus strain in the fiber. So, which is the additional strain. So, additional strain is this, average additional strain will be this much minus the strain that, as there will be a minus plus, it will be plus actually plus the shortening of the matrix. Now, how much the matrix shortened? It was originally epsilon mu, but now it has average strain in the matrix has become half epsilon mu. So, the shortening of the matrix is this much. Therefore, this multiplied by the 2x distance will give you the crack width. So, let us look at this again. This is the average strain increase in the fiber. This is the average shortening in the matrix. Therefore, the crack width will be sum total of this increase in the fiber strain, fiber got elongated, matrix got shortened, gap is the crack width. So, this is the average strain that has been released from the matrix. This multiplied by 2x dash gives me the crack width and the average crack width, and this is simply nothing but this. So, that is the average crack width. So, we just reiterating what we talked about. At failure, actually sigma Cu is equals to sigma Fu Bf, because composite now after that the matrix has failed. Now, if the fiber is snapping, it will be the sigma Fu Bf, whatever is the type of fiber. All right. So, that is how we got the stress strain diagram, and obviously, the strain at the fiber we can find out. Now, strain at the fiber we can find out. Basically, we will come back to this, but let us look at this diagram, strain at this fiber. So, if you look at this diagram, this was epsilon mu when the crack started, then there is a sudden increase, and we said at this point I will have epsilon mu alpha by 2, because total strain in the composite would be the extension of the fiber, because the matrix is within the fiber. So, here is a fiber, matrix is simply within, matrix is simply within. So, length of the fiber, total elongation of the fiber is the elongation of the composite as well. So, strain in the composite strain is simply the total. So, epsilon mu was there earlier. So, plus now average increase in the fiber is half alpha by epsilon mu by 2. So, at this point it is half epsilon mu by 2. Now, we want to find out now what is the strain at this point, strain at this point, strain at this point. Now, the stress difference here is this much, which is this we know is sigma Fu V f, this stress here would be sigma Fu V f, and here it is actually E c epsilon mu, because composite modulus of elasticity multiplied by epsilon mu. So, this is the stress difference divided by, so stress divided by strain is equals to modulus of elasticity. So, modulus of elasticity is E f V f, because it is only the V f V f here. So, this strain additional strain, the strain that is there strain can be written as this divided by E f V f. So, this strain as strain here can be written as the strain here, as I am showing, will be written as sigma Fu V f minus E c epsilon n divided by E f V f, and that is what is that is E f V f. So, this is this additional strain I can find out, and let us see what is the expression for this, the expression. So, that is what we are saying, epsilon mu 1 plus alpha 2, that is at the matrix failure, plus sigma Fu V f, that is the final stress, minus epsilon c epsilon mu E c epsilon mu, that is the the stress beyond this point at up to failure, divided by E f V f. So, that is the additional strain. This will be the sum total of strain at failure, strain at failure. So, and this can be written as simply divide epsilon Fu by E f, you get sigma Fu by E f, sigma Fu by E f, V f will cancel out, I am left with epsilon Fu minus E c epsilon mu divided by E f V f, minus E c epsilon mu divided by E f V f. Now, E c can be expressed as E m V m plus E f V f, that is what we have seen, and if I divide this by E f V f, this will cancel out, and this I am calling as alpha. E m V m divided by E f V f I am calling as alpha, and this is simply 1. So, it is 1 plus alpha into epsilon mu. So, if I see the failure strain, then failure strain I can write as strain at failure will be written as epsilon mu 1 plus alpha by 2, which is at the time of matrix cracking. Then we have seen that is equals to epsilon Fu minus it was E c epsilon mu divided by epsilon mu divided by E f V f, and that we have derived just now as 1 plus alpha into epsilon mu. Therefore, if I do a little bit of algebra out of this, I get epsilon Fu out here, epsilon mu is there everywhere, I get this value. So, this strain here is epsilon Fu minus alpha by 2 into epsilon mu. So, that is the failure strain, but this is for an ideal sort of a fiber which will have strain enhancement. If you want to find out for real fibers the snapping, which is not very important, because most of the fibers do not snap unless they are weak fibers, but we add usually strong fibers. So, they do not snap, but the effect of short and random fiber will always be there. So, short and random fibers, their stress strain behavior is actually something like this, depending upon the type of fiber. If you have sufficient fiber, it might be like this, in some other cases it will be like this, quantity of fiber depending upon quantity of fiber. So, it would be either of this kind or of this kind. For example, steel fiber concrete, it might behave like this. It may not show strength enhancement, but it would show a lot of deformation beyond this, because the fibers can still, after cracking, fibers can still withstand the load to a lower level, but a lot of deformation it will show. So, that is how you get pseudo ductility even in real fibers. All this formulae you want to get for real fiber, then you have to modify them as far as strength part is concerned by putting in this orientation and length efficiency factor, which you have done earlier. So, you have just looked into the crack width for aligned fiber. Just let us look at the and stress strain diagram for aligned fiber, and then for real fiber, because real fiber all this modulus of elasticity for real fiber, the modulus of elasticity here will be multiplied by this, and after that also it may not be able to take the load, which may be less than that. So, the load it can carry would depend upon its EF and the VF content, which could be low. Depending upon that situation, real fiber behaves in this manner, but then they are short random fibers. So, therefore, crack for short fiber we can look into. So, let us say x d is the length required to transfer load sigma m V m per unit area of composite to the fiber, right. So, 2 x d is the crack spacing, that is what we have seen actually, but when you have short fiber, what will happen? One side you may have some length, another side you may have full transfer. In one side you may have full transfer like this, full transfer. One side you may have full transfer like this, because it would not be 50-50 divided in both the direction. It will be it will be divided. So, sigma f u might attain here, sigma f u, but this side it may not attain. So, one side you will have length, because it is unlikely to be even if you have sufficient length, let us say L c to L c, critical length, if you have critical lengths also, but then it is very unlikely that both sides it will be 50-50. Only one side it will have part development strength, development length will not be full. On this side you may have development length plus more. So, therefore, the effective number of fibers one can modify. We had effective number of fibers earlier, n equals to V f divided by pi r square, but now this will get modified by a factor. I can multiply it by a factor, multiply by a factor such that if it is full fiber effective, then this factor is 1, but if it is only part of the fiber effective, then I can take it something like this. I can take it something like this. So, what we are saying, twice pi r tau x d is the length required to transfer full load, which we have discussed earlier, which we have said earlier, it is required to transfer the full load, all right. And this is the n fiber if it was aligned fiber. Now, the number of fiber that will be effective in transferring full load will be 1 minus twice x d divided by L. So, L is greater than twice x d, L is greater than twice x d. So, this fraction, this fraction, if it is 1, then there will be no fiber effective, because it is it will not be, only a small fraction will be effective, because if it is just L c, one side you will have this, there will be not a single fiber will be actually effective to transfer full length on both the sides. No, because it will be just within the space. So, if this is bigger, then a fraction of it will be effective in transferring on both the sides, and the remaining fraction, that is 2 x d by L, again multiplied by L, they will be transferring partly. So, what you are doing here, you assume that they will be either transferring 0 or full length, therefore, you take the average. So, x d by 2 you take. Here it is n is the number of fiber for aligned situation, that is V f divided by pi r square. If this the amount of fiber which will be able to transfer the load on both the sides fully is given by 1 minus 2 x d by L. Remaining 2 x d by L will be able to transfer only half on an average. Remaining number of fiber will be able to transfer, because they will either transfer 0 or they will transfer full length. So, you can take half length x d, and therefore, this is the bond, this should be, must be equals to sigma mu V m, because that is the force that can be sigma mu. This gives us the length, actually gives us an expression for length, which will give us this, because we have earlier done simply twice pi r tau x n, x to x dash we wrote, and n is equals to this, but now we are writing the same thing with x d as a new terminology, using the same thing, sigma mu V m. So, this will be an equation, and this, from this equation, if I try to arrive at x d, because it will be a quadratic equation in x d, x d and x d here. So, x d square. So, x d can be written as something like this, So, x d can be, it will be, it is a quadratic equation written something of this form. So, where x dash stands for a line fiber situation, for x dash we have found out for a line fiber. So, one can write x d will be a function of x d by L. How much is the x d? Gap, the x d is just half spacing between the cracks divided by L. So, that is how you can find out. So, it is a quadratic equation and x d can be obtained in this manner for L x dash etcetera, etcetera. So, it is a quadratic equation and x dash can be obtained in this manner, where L is the length of fiber, x dash is for a line fiber, and you can obtain in this manner. So, if you plot it against, if you plot it L by d against x d by x dash, so when if you plot it, actually you will get a curve like this, it will get a curve like this. So, it will depend upon L by d, because this was a function of L by d, there is a relationship between diameter of the r, the r is coming in here, there is a relationship between r. So, as your L by r increases, this changes, and you can plot it in this manner depending upon L by r. So, as L by r increases, L is the length, by r increases, this is x d by x dash changes in this manner. So, this is the behavior of short fiber, and in such case sigma C u will be length efficiency factor, sigma f u B f if they are aligned, and if they are not aligned, then this will be your for randomly oriented, both this efficiency factor must be taken into account, sigma f u B f, that is what you should be taken into account, the composite strength. So, the composite ultimate strength will be given by this. Failure it will be epsilon mu. Now, if it is less than, if this is less than E c, composite E c into epsilon mu, then you will find there is the behavior is like this, rather than an enhancement, you get behavior like this. If this value is less than E c m c, you find the strength would actually reduce, but deformation it can continue, because it will not splinter out, the fibers will hold it, the crack width will be initially restricted, there will be large number of cracks with small widths and number of them. So, this will be the ultimate strength. So, this will happen when fiber is snapping, but in reality fiber do not snap, because short fibers they do not really snap, and they actually fail by pull out. So, we will come to that. So, number of fibers approximately one can take it as short fiber B by pi r square for 1D aligned, 2 by pi B f by pi r square in 2D random, and number of fibers in 3D random one can take approximately from effective number of fibers in 3D random orientation, this one can take. We have written B f divided by pi r square for aligned fiber, then we have seen if they are short they will not be effective, but we have not talked about the number of fibers. We said the effective fiber which will be taking the load for calculating the crack width, but this is what one can assume roughly the number of fibers, it will be half the number of fiber in 3D random, number of fibers along the direction of the load is given by this effective number of fibers. So, I said that short fiber usually fall by pull out, because the fibers are strong. So, before they can snap, which we have shown earlier, we have given the formula for snapping, nu L nu 0 into sigma f u B f, but that rarely occurs, instead they pull out. And if they pull out, what happens is, supposing there is a crack. So, some fibers, this is your direction of the load, this is the crack direction of the load. So, this is the n number of fibers, just now we have shown the effective number of fibers in a given direction, in the direction of the load. For 1D we said it is B f by pi r square, for 2D it is pi by 2 B f by pi r square, and for 3D random it is 1/2 pi B f by pi r square, just now we have seen. So, these are the number of fibers, and actually they will tend to align along in the crack, they will tend to align along the direction of the pull, but they then gradually get pulled out. Now, this pulled out length, this because on this side of the crack I can have either 0 or L by 2. I can have 0 or L by 2. So, on an average I can assume that L by 4 will be the minimum length. This is larger, this is smaller, this is larger. So, out of the two, the minimum length on an average will be L by 4, because the minimum length can be either 0 or its maximum value of the minimum length about the crack on the one side of the crack can be L by 2. So, on an average L by 4 is the minimum length, and when I am talking of pulling out, L by 4 is the average length of pull out. When it is it's pull out failed by puller out, this much length, it should pull out by this much length, and so L by 4 is the average pull out length. I can assume average pull out length is L by 4, and therefore, for one fiber tau pi d is the parameter into L by 4, that is the pull out force required to pull out one fiber, tau pi d L by 4 is required. Remember, when pull out is occurring, the bond, this actually the tau is quite often it is like this. Initially there is a perfect bond. So, if I plot this tau versus pull out length, then initially it is perfect bond and it will increase like this as the as I try to pull out, they go together, there is a perfect bond. Now, then there is a bond failure, and after that it is a friction which will keep it on. So, the tau might be, I might take this as my tau ultimate or tau tau ultimate, I might take this. So, this tau is that tau which is actually because of friction. First, so because there will be roughness and because of friction. So, actually initially there will be perfect bond. Once the crack has occurred, actually there is some amount of pull out, and this failure might have occurred, but beyond that I will have still bond available and pull out would be there. So, I take this value which is the lower value as the value for bond out, pull out strength or bond strength for pull out. So, tau pi d into L by 4 is the force required to pull out one fiber, and for n fibers I will require n tau pi d into L by 4. So, this is my sigma cu. So, all the fibers you have to pull out, this will be my sigma cu. Now, n is the effective number of fibers, it will depend upon type of alignment I have. So, n is the effective number of fibers. So, therefore, it will be sigma for one for the fiber pull out force we have seen, sigma cu composite is like that. So, B 4 B f tau pi d L over by 4 pi, I get the sigma f, the stress in the fiber. So, stress in the fiber corresponding to the pull out is basically sigma f B f and B f divided by 4 pi r square or pi d square by 4. So, sigma f B f is the stress, and I said it is n tau pi d L by 4. It was n tau pi d L by 4, because tau pi d into L by 4 is the force for 1, and this can be written as V f by pi r square or pi d square by 4. So, I write 4, this n can be written like this for aligned fiber situation, pi d L by 4. So, if it is aligned fiber situation, this pi will cancel out with this, d will cancel out with this, and I will be left with B f will cancel out from this side. So, I will be left with sigma f is equals to tau L divided by d. So, stress at the pull out is sigma f pi L by d, sigma pi f pi L by d, right. So, stress at the pull out is this. So, sigma Cu, therefore, composite stress the composite strength can be written in terms of sigma f into V f, and the stress in the composite is V f tau L by d, because sigma f is this for 1 d aligned, for 2 d aligned, V f is for it is all aligned fiber, this is the effective number of fibers is this. So, sigma f stress in one fiber is this, and for all the fiber 2 d random and 3 d random sigma cu can be written like this. So, when you have fiber snapping, the force, the tensile strength of the composite will be governed by the pull out force, because this is the tensile force in the fiber. The matrix has already failed, the matrix has cracked, and after that the pull out is occurring, and this is the stress that the fiber can withstand now, that is limited by this, the pull out force. So, pull out force in one fiber is this for effective number of fibers. So, for 3D random it is half V f tau L by d, that is the composite strength, because the pull out will govern, although a sigma f u has not reached. Sigma f is governed by the pull out force, because it will pull out, and the stress that is attained, that is the stress the composite can take it multiplied by V f. So, that is how we find out the pull out force. So, this is all in axial situation. This is all in axial situation. When I have a direct tension, all this has occurred. Now, let us look at the flexure. How does it behave in flexure? So, if you look at the stress strain diagram, let us say just before that, let me look at the stress strain diagram, then this could be my E c, E c, then there may be at the crack it will look like this. When occurring pull out is occurring, then there is an increase, and after that it could be half V f tau L divided by d, tau L divided by d if it is 3D random, and if this value is more, because it will fail by pull out, usually they are not. So, you might get it something like this is the ultimate somewhere here, but then lot of basically the matrix fiber will go on extending, matrix is inside it, fiber will go on extending till a situation like this has arisen, till the gap has become the gap between, till the gap has become so large such that my fiber is this side, the length is more, his side the fiber has just come out, So, this is the point of failure. So, it will actually L by 4 at least it can on an average L by 4 deformation it will definitely show. So, depending upon the situation, but all the fibers should be there. So, it will be a random scenario. Many of the fibers possibly will show up here, many of the fibers, and the last fiber has come out actually, or it will snap, because there is only one fiber to extend the length. So, there could be some snapping also. So, it will actually behave in this manner, and the ultimate strength that we are taking is, supposing I take it simply like this. So, stress strain behavior, neglecting, idealizing it something like this, this will be simply sigma f V f, which will be equals to half V f tau L by d. So, I can safely assume a long deformation, long extension with this kind of strength available. So, long deformation I can assume, long deformation, long elongation I can assume. So, stress strain curve I can idealize like this. Now, in flexure we are talking of improvement of the matrix itself, that is why we are talking of modulus of rupture. As I mentioned earlier that we do not talk, it is not the same thing as conventional rebar, that is not the case, it actually improves the material itself, and therefore, we are talking of modulus of rupture of the concrete, and this is how we test the modulus of rupture 1/3 loading L by 3, this is L by 3, this is L by 3, you have actually 50 bar in Indian standard with 50 centimeter, with this as 40 centimeter, and 1/3 and the P you apply, this is P by 2 and this is P by 2, and you get cracks like this, modulus of rupture test that we do, because this is your epsilon compression and this is epsilon tension. So, this is the and this is the depth of neutral axis at failure, crack occurs. So, this is the modulus of rupture test we know, and we are trying to see how modulus of rupture changes with the fiber. So, modulus of rupture for 3 types of stress variation I can assume. I said that I can assume simply this type of stress variation, compression stress variation will be like this, tension in this zone. So, lower strength, actually strength is reduced significantly. In this one what I just showed, ideal but ductile, lot of pull out is possible. Here it is strength enhancement, enhanced strength, but in any case the deformation available is significantly large, strain available, corresponding strain available will be significantly large. So, strain available is, so moment of resistance for no fiber reinforcement, just so what is available is the strain available will be large, that is what we will see. So, let us look at moment of resistance for plain concrete. This is triangular distribution stress diagram, this strain distribution and stress distribution both we take triangular. So, this is your sigma compression, sigma tension, tensile strength, modulus of rupture, we assume stress and not real stress strain diagram variation we do not take. Actually, real will be something like this in case of concrete, but then we do not take it, we take it triangular stress distribution for calculating moment of resistance. So, we can here also we can adopt the same principle and just see how the modulus of rupture change. So, in this case C and T and this distance is 2/3 d, right. C acts at here 1/3 d by 2 and this is 1/3 d by 2. So, this is 2/3 d, neutral axis is at the center, we assume sigma compression is equals to sigma tension of the plain concrete, and then I can calculate this out as sigma t because this will govern, failure will not occur here, this will govern, this will failure will occur here. So, half sigma t into d by 2 half sigma t, half of the sigma t. So, sigma t into d by 2. So, it is actually sigma t half sigma t into d by 2, that is the triangular area sigma t into d by 2, and of course, the width we are taking as unity, this multiplied by, so sigma t d divided by 4 multiplied by 2 d by 3 lever arm gives me sigma t d square by 6. Well, this you know very well. So, that is the moment of resistance for plain concrete. Now, let us see fiber concrete. Moment of resistance for fiber concrete. Well, first let us look at the diagram. Now, what we said was the strain will be very large. In fact, the strain diagram, if I plot it, it will be very large here, large strain diagram. Strain diagram will be large, and what I can do is strain will be very large strain, because now it can deform quite a lot, but the stress could be very small sigma c u. So, my neutral axis goes up significantly, and I can now calculate out the moment of resistance. So, neutral axis strain would be very large, because it can now deform quite a bit. So, correspondingly neutral axis will go up, there will be a lot of rotation available, because the crack will not simply open up, the fibers will restrain the crack opening, and therefore, it is actually will ensure that there is a lot of deformation prior to failure, pseudo ductility, and my this the stress block in the tension zone will be something like this, assuming this is the smallest one sigma c u, the least value as I showed you, idealized one, and approximately one can take this as d by 4, because d by 2 it was, now I take it to be d by 4 at failure, strain has increased at the bottom, strain has increased so much, d by 4. So, therefore, this is d by 4. So, this is 3/4 d. So, if it is 3/4 d, this is sigma c u into 3/4 d, 3 by 4 d, that is what I am doing. And how much is this distance? This is simply, this distance is 3 by 8 d, this is 3 by 8 d, and this distance is actually in a triangle, this is the center point of the triangle. So, this was my 1/3 d, this is 2/3 d. So, 2/3 d by 4. So, if I d by 4. So, if I add this up, 1 by 6 d plus this is 1 by 6 d plus 3 by 8 d. So, this will be actually 24, and 6 is 4, 8 is 3, right. So, 3 9 plus 4 is 13 by 24, 24 d. This will be 6, this will be 6 4s are 24 and 8 3s are 24, therefore, 9 plus that makes it this. So, 13 by 4 d, and this will turn out to be sigma c u 13 by the 4 is there So, sigma c u 13 by 24, if I calculate out how much this is comes to sigma c u 32, this is not 30, this is 32, this is 32, please correct it, this will be 32. So, for same moment of resistance, this is 32, this is wrong, this is 32. same moment of, so this will be 32, 13 by 32 d square. So, for same moment of resistance sigma Cu 13 by d square. So, this comes out to be 4, 0.41. So, this was my sigma t, this is 6, this will come out to be actually this will come out to be d square will cancel out. Now, if you have to have same moment of resistance, if I have to have same moment of resistance, please cancel this out, it is not 24, it should be 32, it should be 32. So, this should be, this is 24 all right, this should be 32. So, this should be 32. So, it is 13 by 32 d square. So, sigma Cu moment of resistance is given as sigma Cu 13 by 32 d square. Now, if this has to be same as same moment of resistance, if I want to get, then I want to get a relationship between sigma Cu and sigma t. So, the d square will cancel out, this is 16 and this is 39. So, I will have sigma sigma Cu is equals to 16 by 39 sigma t, 16 by 39 sigma t, roughly 40. If you assume it, you can easily show that it is actually 0.41 sigma t. So, sigma this, so to have equal moment of resistance, what I need, this sigma Cu I need only 41%, 41% of the tensile strength of the concrete. So, even if there is no enhanced strength enhancement, then also I will get flexural strength enhancement, because to have same moment of resistance. Now, if it is if it is more than 41% of the sigma t, supposing it is sigma t, I will get actually 200% enhancement in strength, because it will be supposing sigma Cu is equals to sigma t, then moment of resistance will be simply moment of resistance ratio will be given as sigma t 13 by 32 d square divided by sigma t by 6 d square. So, you cancel this out, this cancel this out, and you will get actually 6 into 13 divided by 32. So, moment of resistance ratio of moment of resistance divided by 32, which means that this is 3, 39, this is 16. So, 39 divided by 16 will give me how much? 2 point, it will be 32. So, 70, 2.4 something something. So, you can see that if the tensile strength of the matrix and the ultimate tensile strength of the composite is same, I get a flexural strength enhancement, moment of resistance enhancement 2.4 times. So, that is a great thing, that is actually that is where the advantage of fiber concrete is. So, thus for post cracking flexural strength enhancement, sigma Cu need to be more than 41% of the matrix tensile strength, and if it is same as sigma t, you will get more than double, 2.4 times, or 4, 5 or something, whatever it is, very large, 1 by 0.41, I mean 1 by 0.41, that much time increase in the nearly to large increase in the flexural strength. So, even if it maintains same, but actually it does not maintain, it is lower. So, you always get a flexural strength enhancement, even though you may not get a direct tensile strength enhancement. Direct tensile strength enhancement is difficult in short random fiber. Compressive strength really do not improve, because compressive strength is governed by tensile failure. So, it actually does not show any improvement, but flexural strength there is a significant improvement, right. So, nature of the stress diagram may vary, of course, depending upon type of fiber, as I mentioned. For example, some fiber might show like this, 0.41 should be here, then it is good enough for me, it is good enough for me, just 4.1 has to be here, and in some cases if it is 1, then I will get so much of increase, actually increase in the flexural strength. Therefore, flexural strength of the concrete matrix get improved by putting in fiber, although direct tensile strength may not increase, because direct tensile you can add only 1-2%, very small quantity, volumetric or mass percentage, you can very small 1.5% you add, because beyond that adding becomes very difficult, mixing becomes difficult, there are some effects which you will come to. So, therefore, that becomes difficult. So, you can't add that much, but even if so, and therefore, tensile strength enhancement may not be significant. Short random fiber, the orientation and the shape, orientation and the length, they start actually reduce down the strength. Further they can pull out, this can reduce down the strength, but even if it is 0.41, you will get same modulus of rupture. It is something like this, you will get much better. Okay. So, that is the basic understanding of why flexural strength is enhanced in fiber reinforced concrete. MR of fiber concrete comparison, if you see, this is what I was just telling you. Now, to prevent compressive failure, this already I have told you that it is 2 point something, 39 by 16 times. So, to prevent of course, compressive failure, the other criteria, composite should not fail in compression. So, if it is, if should not fail in compression. So, what is the compression load? This is sigma compression, this is L d by 4. So, this is half d by 4 into sigma compression, that is the stress block, right. That must be equals to the tensile failure occurs by this. So, at failure sigma compression will be this much, at failure the compression will be this much, at failure compression will be this much, compression will be this much. So, under this condition sigma compressive should be more than 6 times the, if you calculate this out, 4, this is 2. So, it is C. So, sigma Cu, sigma C comp by sigma Cu will be given as 6. So, it should be greater than 6. The the compressive strength should be greater than 6 times greater than sigma Cu, otherwise there could be failure, otherwise there could be failure. But normally this occurs, because we have seen earlier that it could be 8 times easily. So, therefore, this occurs. So, this is a prevent compressive failure, this ratio must be maintained. This ratio must be maintained, right. So, this ratio must be maintained. So, what we have seen so far? We have seen so far that tensile strength enhancement may not be significant, flexural strength enhancement is significant, crack arrestation do occur, and we get pseudo ductility, all these properties enhancement we have seen. Let us see what are the type of matrices we use. Well, high strength concrete, normal strength concrete, this is the matrix we can use, but slightly you have to define the mixed design differently. In fact, you can use microfiber, engineered cement composite, which I am not discussing in a big way, engineered cement composite. You can actually put in microfiber and the length small fibers actually and enhance in a very high strength system. People are thinking of adding nanofiber, which might increase the strength at the nano level. So, tensile strength might of the matrix might increase so significantly, because nano crack it will arrest. Microfiber can arrest micro cracks. Okay. So, the fiber high strength matrices, very high strength matrices, also with say polymer composite rebar together with very microfiber, people are attempting to make composites which can be used for very high strength, high end users and so on and so forth. Normal strength concrete we know, and we can always use fiber reinforcement for flexural strength improvement, and pavement for example, where flexural strength improvement is a necessity, we can use them. Places where I need flexural strength enhancement, we can use this fiber composites, fiber reinforced concrete in normal strength concrete. But mixed proportion of this one is different. You just can't make a normal strength concrete mix and put the fibers, you will have all kind of trouble. We will just look at that. Types of fiber that you get, varieties of fiber you can get actually, fibers of varieties of, for example, S glass, E glass, types of glass, alkali resistance glass. This is Kevlar 49 is a branded product, aramide actually. Then carbon high strength, boron, carbon high modulus, lower strength. There can be varieties of fiber possible to be used in reinforced concrete reinforcement, other than of course steel, polypropylene, polyester. So, these are several of them, polypropylene and polyester, they are being used today for shrinkage cracks and all, because see this is your steel, high yield steel, mild steel idealized stress strain diagram is here, mild steel idealized stress strain diagram, high ductility polypropylene, high density polypropylene, sorry, high density polypropylene, low density polypropylene, and this is polyester, then glass, high modulus polyethylene. There can be several types of fibers that can be used depending upon their properties, but you see the steel of course gives you high modulus. So, low modulus you have to once you have understood the behavior, therefore, you can think of how to use them, which way, how the way they will benefit, and so on and so forth. So, you have looked into the fundamentals and properties of some of them. What properties are important? Diameter, fiber diameter, density, diameter, density, modulus of elasticity, tensile strength, elongation, coefficient of thermal expansion. These are important properties, and some of these properties are, some materials are available in literature, a part of it from taken from literature, actually Hannon's book, this data. So, E glass, density, modulus of elasticity, you can see these are in GPa, tensile strength you can see. So, for example, this has got a high modulus of carbon, high modulus type, carbon high strength type, low modulus, but the strength is tensile strength is 2.8 GPa, that is 2800 megapascal, and so on and so forth, and Kevlar 49, these are the kind of properties. Shape of the fiber can vary, shape of the fiber can vary. For example, you can have hooked, crimped, and varieties kind of cross section, rectangular, all kind of hooked fibers, all kind of, because bond strength is important, because I said that frictional bond after slip that occurs, therefore, which I showed a diagram earlier. So, bond strength is very important, therefore, you can make all kind of fibers and use them, right. Now, in the plastic state, we normal fiber concrete we have to test by only VB test, but that also VB test, we test with VB test, because its slump is, it will not have very low slump. So, what is seen is that VB time tend to increase with fiber content, depending upon L by D. Higher L by D, VB time is least, depending upon this is depending upon L by D, this is the highest L by D, and this is the next, and so on and so forth. Now, what happens is VB time increases significantly for high L by D with small quantity of fiber increase, while this L by D can withstand quite a lot of fiber content to have a VB time small enough as 1 second. Supposing I say that 1 second is the time, or 10 second is the time, good enough for my VB time, or 20 second is the time, you find that this is attained at much lower fiber content for higher L by D. So, L by D governs the VB time. It is important to understand. Higher L by D means lower VB time. Also, the spacing of the fiber aggregate, because of the size of the aggregate. So, smaller sized aggregate, spacing of the fiber is better. So, MSA, higher MSA, spacing of the fiber is poor, and you will have fiber spacing is non uniform in this case, all fiber will try to bundle out and results in a kind of balling or formation of bird's nest. So, workability is a function of all this, So, you have MSA, higher MSA, again same sort of curve you see, less percentage of fiber it can tolerate for good workability. A empirical formula for steel is given as that the fiber content by mass or weight as a proportion of the matrix should be less than 600, 1 minus Ag divided by L by D. So, you have L by D higher, the fiber content you can withstand is lower, right, and Ag is the fraction of coarse aggregate in the system. So, higher the more the coarse aggregate in the system, less the fiber it will tolerate. So, you should have more mortar, more paste. So, it requires more mortar and more paste. Plastic fibers reduces bleeding and plastic shrinkage cracks, that we have seen. Durability depends upon type of fiber. Steel can corrode, but low diameter to cover depth, so because but low low diameter, but this is low, corrosion is low, as diameter to cover depth is small. We have very small diameter, cover depth still is large, very large, and therefore, it is small. So, plastic fibers are also inert, they do not corrode. Steel fiber can corrode, but fiber concrete does not show that much of corrosion. Unless it has cracked and got exposed, it will not show that much of corrosion. Actually, micro cracks will not show that, but then you have a cover, put a cover which is not fiber, it will. Glass fiber shall be alkali resistance, otherwise cement materials can attack them. It should contain more paste, about 70% mortar is a good thing in this one, 30% aggregate. So, you see you require more paste and mortar, and hence mixed proportion should be specific. Many a times people tend to do a mixed proportion for concrete to get strength and then put fiber, this will not work. You have to have specific mixed proportioning for this purpose, and we have then thus we have understood in nutshell the fiber concrete. Let us look at another concrete. We have looked into self compacting concrete, which is free flow. Now, look at the other concrete, which is actually high slump. So, it has got very low consistency represented by no slump condition, 0 slump condition. This is called roller compacted concrete, placed by asphalt paver in pavement and compacted by high density vibratory roller used in earth or rock fill construction. So, in case of pavement, you can put it by asphalt paver type of thing. In case of course, mass concrete, you have to carry it by truck, non agitating truck generally, and segregation of course, is an issue then, but used finally compacted by vibratory roller. So, it has to be dry, absolutely dry, 0 slump. Compaction of water content governs the strength. So, therefore, it is a compaction and the amount of water content, you are treating it like soil. So, water cement ratio is not the issue here, but compaction and water content is the issue. Shall be dry enough to support roller and wet enough to have uniform distribution of paste. So, that is the basic idea. You have paste distribution well, sufficient paste and well distribution of paste, just wet enough to get maximum compaction, and but it should be dry enough to support the roller. PB apparatus with load on top is what we use. With a surcharge you used, and its MSA can be 75 to 100 mm for testing the workability. We will come to that a little bit. I can have MSA 75 to 100 mm for mass concrete, 20 mm for pavement concrete, which can be as strong as 30 MPa or 30-40 MPa. You can get 30 MPa is easily attainable in Indian scenario. It will have high fine content, strength depend upon density. You can get around 30 MPa easily. Batching mixing, cylinder strength 30 MPa is not difficult if you use ACI method of mix design. Batching and mixing is same as that of normal concrete or mass concrete for mass concrete, and then segregation problem is there if you are taking it by truck. It is placed in layers of 20 to 30 centimeter and spreaded, it is spreaded with spreaders. It is generally spreaded with spreaders, spreaded with spreader. So, cylindrical surcharge could be of this kind for pavement concrete, typical BB test, and you put a surcharge here. So, this is your surcharge are here. These are the surcharge. Let me use red color. These are the surcharge. Additional surcharge you put, do the BB test. ASTM 1170 gives you the idea. So, BB test with surcharge, that is the idea, and RCC requires no forms, requires no conventional finishing. Therefore, big advantage. Less cement actually in this you can design it for lower cement in fact. So, it is Proctor's compaction what governs the strength, and you can use ASTM D1557. Selected combined aggregate proportion, packing density is important here. You pack the aggregate pretty well, so that paste content is reduced. So, then you fly ash around 25 to 30% easily you can use and must use. And mass concrete obviously you are going to use them because of heat of hydration. So, fly ash, you use this kind of thing. So, all specific cementitious material, and then put them together and do a Proctor's compaction test by varying water content, right. So, this is the Proctor's test, Proctor test, strength and density relates. There will be Proctor test actually, Proctor test you will get here, right. Proctor test you get here, the variation you get something like this, moisture content versus density, dry density. You plot it like this, moisture content, choose the optimal moisture content 6% or 5% as per the methods that are there, and then that would give you the maximum density. So, density versus strength relationship is like that, density versus strength relationship is like that. So, 7 day strength, dry density, well it could be better for better concrete. So, therefore, what we have looked today? We have looked into flexure of fiber strength concrete, types of fibers that we can use, and lastly roller compacted concrete. So, roller compacted concrete to end, just let me summarize. The roller compacted concrete is a zero slump concrete, generally can be used or generally used in pavements as well as in mass concrete dams, and it might turn out to be cheaper, basically because you are doing away with the formwork, cement content could be less, and then same the equipment that you use, you do not require special equipment, same equipment that you use for pavement construction or for mass concrete construction, you can use the same one. So, with this we conclude our discussion on fiber concrete and roller compacted concrete and lecture 5. Thank you for hearing.